Hello, everybody. My name is Diptajyoti Mukherjee, and I'm here to talk about the evolution of massive black hole binaries and merging nuclear star clusters, which is based on a recent work, which you can find at this archive link. Before I even go into talking about massive black hole binaries, we know that in the hierarchical paradigm, galaxies grow via merges. That's how we know that nonlinear structure in the universe forms. So if you have two galaxies that are merging in this, as shown in this nice simulation, you can imagine if they contain massive black holes at their center, during the merger process, the massive black holes will get a chance to get closer to one another and form a binary. And I just wanted to give you an idea of the impressive range of scales involved in this problem. We go down from kiloparsecs to less than parsecs, and I want to emphasize that these are not theoretical objects that we just expect from our simulations. We have actually seen them in nature, as this picture of a double quasar that the Hubble Space Telescope took in 2021 tells us. Now, why would we want to study these objects? Well, massive black hole binaries are touted to be one of the strongest sources of gravitational waves in the universe, which makes them a very important LISA source. Now, despite being such massive objects, we don't really know how these objects form and assemble or evolve over time. So we believe, or we hypothesize, that by detecting the gravitational waves from such objects, we can astrophysically interpret what's going on inside the galactic bulge and galactic environments, because the dynamics of these binaries is so sensitive to the environment in which they're embedded in. Thereby, in order to maximize LISA science output in the next couple of decades, we need better understanding of how these objects evolve and how these objects merge over time. Now, the evolution of these binaries can be divided into three distinct stages depending on the length scales involved. In the kiloparsec era, the massive black holes are embedded inside their galaxies, and the galaxies evolve because of dynamical friction from the surrounding media, which can be because of dark matter or gas. Now, once the galaxies merge, they merge into a single galaxy, which I'm going to call the host galaxy. And after that, once the bound binaries form, the evolution takes place not just due to dynamical friction, but due to stellar hardening. And it's very sensitive to the environment in which this binary is present. After further hardening, we can reach down to milliparsec scales, where dynamical friction is inefficient, and we evolve because of stellar hardening and gravitational wave emission. Now, the uncertainty in all of our simulations comes from these two eras, the parsec and the milliparsec scales, where it's really hard to resolve, dynamical friction or stellar hardening. And as I'm going to show in the next slide, we don't even resolve these processes properly in cosmological simulations where we derive LISA rates from. On top of that, we encounter uncertain timescales and uncertain mergers because of issues like the final parsec problem, where binaries can even stall before they reach the gravitational wave emission phase. Now, the issue with cosmological simulations is that they cannot resolve anything down below kiloparsec scales, because cosmological simulations are so massive, you cannot go down to parsec or milliparsec scales, thereby us needing really high resolution n-body simulations to understand what's going on in this era. Now, I mentioned that the dynamics in the parsec and the milliparsec era is very sensitive to the environment, the host galaxy's environment, and at these eras, you can find substructures inside the galactic bulge that can affect the evolution of these binaries. And one such substructure that we are interested in studying is what's called a nuclear star cluster. Well, why would we want to study nuclear star clusters? Well, we found that from previous studies that 90% of galaxies containing a stellar mass of like 1 billion solar masses contain nuclear star clusters. So they're present in a lot of places. Sometimes these nuclear star clusters can contain massive black holes at their center. So we speculate that 50% of Milky Way-sized galaxies should contain a nuclear star cluster and a massive black hole at their center. Recent studies, simulations that have been done by Ogia et al. Have shown that nuclear star clusters can greatly accelerate the evolution of these massive black hole binaries to the gravitational wave dominated phases. In particular, these sorts of simulations are extremely robust, and Ogia et al. Found that this is extremely efficient for merging binaries that are really low mass ratio binaries. So in binaries where the secondary is very low in mass and where traditional dynamic friction would be inefficient, and you would actually in some scenarios end up with stalled binaries, as previous simulations have shown. So thereby, in our work, we are motivated to study how realistic models of nuclear star clusters, and I'm just going to explain what we mean by realism. So in our models, by realism, we mean the inclusion of a mass spectrum, because previous studies have done their simulations with a uniform mass function. So we are interested in studying how a mass spectrum affects the dynamics, in addition to increasing, the particle numbers from previous studies. So we require a code that can not only do high resolution n-body simulations, but that needs to be sufficiently accurate, and it needs to be quite fast because we don't want to wait months for our simulations to finish. So we wrote one such code in 2021 called Tai Chi, which uses a way to solve force called the fast-multipole method that is as accurate as direct, n-body summation that you might expect. Requires like n squared, pairwise force calculations, but does it in O of n operations. So it's a really fast code that fulfills all of our other accuracy criteria as well. Now, when generating the models, we are interested in massive black holes that fall inside the LISA band. So we set our primary mass to be 1 million solar masses, and we generate secondaries with masses of 1.0, 0.1, and 0.01. Now we embed these massive black holes inside realistic nuclear star clusters with a mass function. We don't use any general initial mass function. Rather, we simplify our mass function into a 2-component mass spectrum where all of the masses that are about, on an average, a solar mass or above, close to a solar mass, can be represented by these MS particles. And anything that's about 10 times more massive than that, so about 10 solar masses, is represented by a population of BH particles. Now we are interested in investigating 2 types of nuclear star clusters, the non-relaxed and the relaxed models, because nuclear star clusters can undergo collisional relaxation. So you can actually have mass segregation where the heavier population actually segregates to the center of the nuclear star cluster. And we are interested in investigating how that affects the dynamics of the massive black hole binary. So in the non-relaxed models, you have a inner density cusp that falls as r to the negative 0.5. In the relaxed models, you actually form a Bacall-Wolf cusp where the density profile of the BH particles falls as r to the negative 2, and the density profile of the MS particles falls as r to the negative 1.5. So once we generate these nuclear star clusters, we set them about 20 parsecs apart from each other in circular orbits and in eccentric orbits in some instances, and we let them merge and see what happens over time. So just to give you an idea of what actually goes on in our simulations, here I've presented an evolution of like a nuclear star cluster merger with massive black holes inside over the course of 2 million years. We let our simulations run for about 10 million years, but here I've presented a snapshot. So from the outset, you can see that the clusters merge within 1.5 million years, and by 2 million years, we have formed a hard binary of the massive black holes. Just to give you an idea of how impressive the length and the time scales involved in this problem are, we're starting from a separation of about 20 parsecs, and we're going down to milliparsecs in just like 2 million years. So thereby making it a very efficient source to, harden the binary. And we see this across all of our mass ratios. So we don't just see that in, Q equals 1.0. We see this happening across our simulations where you can reach milliparsec scales within 2 to 4 million years. Now here I've presented, like the evolution of orbital parameters, but I want to focus on the last row here because that's where the interesting stuff is happening. So here in the last row, let me zoom in a little bit. I have presented the evolution of the inverse semi-major axis as a function of time. The reason why we're interested in the inverse semi-major axis is because the binding energy of the binary is proportional to its inverse semi-major axis. So let me demarcate the hard binary phase, the pre-hard binary phase from the hard binary phase. So the pre-hard binary phase is the one that's shaded in blue, and the hard binary phase is the one that's shaded in yellow, demarcated by the hard binary radius. So at the outset, we see that in the Q equals 1.0 scenario, the non-relaxed model is actually losing energy faster than the relaxed model, which is sort of different from what we would expect intuitively because the relaxed models have a denser cusp. But we see that, curiously enough, the trend is changing over time. And in the Q equals 0.01 scenario, the relaxed model is losing energy faster. So we are kind of curious, and we ask the question, why does this trend change over the mass ratio? So in order to investigate that, we actually need to go back and see what's actually happening to the density function between relaxed and non-relaxed models. And we notice something really interesting. We notice that in the relaxed models, the density is actually lower below, like above some radius of, this truncation radius of 0.1 parsec than the non-relaxed models. And this is something really interesting, and that occurs due to a physical process. So in 2012, this was investigated, and it was found that because of the segregation of these heavier BH particles closer to the massive black hole, they dynamically heat up the MS particles, or the lower mass particles, leading to a lower density in the relaxed models, which is very curious, thereby leading to a more inefficient, dynamical friction phase for the Q equals 1.0 scenario in the relaxed models. That doesn't happen for Q equals 0.1 and 0.01 because as soon as you pass this threshold radius, you actually get more efficient dynamical friction and scattering energy losses, thereby showing that, the trend, why that trend evolves over time and why we actually get, a faster evolution in the Q equals 0.01 scenario. Now, not only are we interested in the evolution of the inverse semi-major axis, we are also interested in the evolution of the eccentricity because we know both of those play a role in determining the gravitational wave timescales. So here we have an eccentric model, and we have compared how the eccentricity evolves between non-relaxed and relaxed models. So we find that non-relaxed models demonstrate higher eccentricities. And this is because non-relaxed models on an average have a lower density than the relaxed models. And we know that dynamical friction tends to circularize. So since dynamical friction is more efficient in close to the massive black hole binary, in the non-relaxed models, in the relaxed models, you find that, the non-relaxed models actually end up with a higher eccentricity because in the relaxed models, the dynamic friction circularizes the binary. So all in all, saying that we should be expecting non-relaxed models, the massive black hole binaries embedded in non-relaxed models, to merge faster. And that's what we see across our simulations. The non-relaxed models have merged faster in all cases. But here, I want to point to you that in all of our cases, the binaries merge within a Hubble time. In fact, the longest time scale that we have is 650 million years for the relaxed scenario for Q equals 1.0, which is less than 1/10 of the Hubble time, thereby indicating that, nuclear star clusters are a very promising source of, gravitational waves. Now, we cannot actually implement these in situ high resolution n-body simulations in current day cosmological sims, because even though they're kind of fast in relative terms, they're still really expensive. So what we are proposing to do in our future work is to take a grid of simulations, so with different initial parameters, changing the mass ratio, the initial eccentricity, stuff like that, and feeding it into a neural network to construct sort of like an MBH evolution emulator. Emulators are nowadays coming into the foray, and people have started looking at emulators to emulate n-body dynamics, and we seek to continue this work in the MBH evolution field. So we can actually implement better models informed on high-resolution n-body simulations rather than some sort of analytic formula that is currently used in cosmological simulations. So all in all, I just wanted to wrap up with a set of conclusions that we were able to obtain from our study. So we were able to ascertain the differences of the massive black hole binary evolution between the non-relaxed and the relaxed models. And we showed that, in the non-relaxed models, the merger process is faster than the relaxed models. We showed that nuclear star clusters are a very promising source for gravitational waves. So we should keep that in mind, looking for looking at LISA sources. We also presented Taichi as a very effective n-body code for simulating all these sorts of problems. Taichi is a code that is in development, and we seek to make it even faster, taking it for even higher resolution nuclear star cluster galaxy simulations. And we discussed potential ways to improve cosmological simulations informed on a grid of Taichi simulations, so that for cosmological simulations we are better able to predict LISA rates, which are currently which differ between simulations within like a magnitude. So with that, I would like to thank you for listening to my talk, and if you have any questions, please contact me using my email link, or I hope to talk to you during this conference. Thank you.